Hello. Moment in motion today from a quiet study of Ross Finlayson here in Seattle, Washington these days. It is a pretty quiet study. It has no real digital electronics operational, though there is a watch, I suppose. And it's pretty much open to the elements for 10 or 15 years. It's has the sounds of the city. It's under a usual path of airplanes. There's this noise of the stadia from time to time. But this little corner of the place is about all that is like that. And it's pretty quiet, usually as otherwise, in terms of the idea of a chance to use it as this little studio of sorts to record these podcasts with the goal of talks and discussions, a monologue of sorts, but in a longer dialogue of these ideas of the foundations of mathematics and physics, which for various sorts theorists have a lot of compelling and beautiful sorts of attachments for their own study in a world of feuilletons, a sort of cultural association with knowledge for its own sake. And not just that, but association and attachment to the canon, our Western canon thoroughly or largely, but the world canon of reason and inference, and that the foundations of mathematics and physics is also the foundations of logic and science. So these are the kinds of things that I really enjoy, and kind of as was the phrasing from one of the earlier talks, it's like, in terms of the ontological commitment that one makes to a theory, what is belief in a theory, that the goal of foundations is a result of something that's pretty simple, yet still what results so thorough. And so from the very beginning, it kind of has to be this dialectic, and not just the usual sense of the dialectic is Hegel's dialectic. There's a thesis, there's an antithesis, something's missing from the thesis. There's a synthesis to bring these together. This fuller dialectic is also what's involved, that it's both ways from that there's complementary duals always about that it's always revolving these sorts of usual notions. So today it's still about meters per second or seconds per meter. In any sense of motion, when it's non-zero, then it's, well, how many seconds per meter? It's the inverse of meters per second. But when it's 0 meters per second, then that's infinity seconds per meter. How can that be? Does it just not exist unless there's an infinite? Well, yeah, that's basically the idea, is that there is an infinite. It is in the numbers. If in the projective space of the numbers, that has to be arrived at via the deductive, a dialectic, vis-a-vis that otherwise it's let out is just kind of beyond the horizon that we can see. For our senses, for our phenomenological, what is the phenomena of the senses, the qualia, or the way it's interpreted, that for something like the noumenal is the idea of that which is only in thought, that things are only phenomenological or only noumenal. And the idea is that this object sense, word sense, number sense, time sense bridges right between the phenomenal and the noumenal, and is available to our model physicist who only has the phenomenal. He can't think outside the box, and he only has the phenomenal. So equipping him with an object sense, and a number sense, and a word sense, and a time sense, for this notion of the infinity, a mathematical infinity, a real infinity, is about the greatest boon that then he can arrive at, as long as that stays consistent, that it's a wider milieu with what's necessary, so that you can arrive at deductively when there's the inductive impasse either way, that there's a sort of crevasse in the middle, which neither side can bridge, making a points into a line or a line into points. That somewhere in the middle, it gives both ways. The meeting in the middle of nowhere, just courtesy why deduction is necessary to arrive at this, where then otherwise oftentimes in linear curriculum is presented that everything is only as for forward induction after axioms. So here it's the axiom is or principles include this inverse, which is necessary. Now, if there's one example of that I feel is about simplest, is that you got Zeno's arguments for and against motion, continuous uniform motion. Right? So usually this is the arrow, the idea of the arrow, and the arrow reaches a target, and it only gets half the way there, and half the way there, and half the way there. And algebraically or formulaically, that's an infinite series called the geometric series, because it's in terms of constant coefficients of inverse powers, here of the inverse powers of 2 and coefficient 1, summing the inverse powers of 2 equals 1. So we say, well, that would be an infinite thing. We can't do infinite things because we have bounds, and we can't, we don't have any particularly given number of distinct instances in time, although the time itself is exactly the same way. But the idea is that so if it goes from 0 to 1, its limit is 1, then that we say, well, that's close enough. But is it really? Because you just imagine you just split that in half and say it goes from 0 to 1 and 1 to 2. To get to 2, it had to get all the way to 1. It had to complete the sum. So that's about a most usual sort of direct deductive result, that it is so that the limit is the sum. Now, it is also so that that's a particularly contrived thing with its bounds of symmetry. It has its milieu, the geometric series that sums to exactly 1 in the infinite limit. So it's not just the limit, and it's not just as arbitrarily close as you need to get. It's the infinite limit, and it is its bound, right? To then proceed to the next in a piece, in a pace, and da-da-da. So I find that kind of fulfilling, at least to establish that, yeah, there must be at least some kind of infinite in the numbers, and everybody knows that. They just call that infinity. And of course, everybody has known infinity, the word, since grade school, and it always means the same thing. It means it's bigger than itself, and it just means that it's great, and everything about it is pretty cool, and it's one of the most wonderful words in the English language, because it's so fulfilling of all these different things that result from the ambiguities of quantification, or the Sputniks of quantification. It's a Russian word. It means companion, like the first satellite was called Sputnik, and what it means is like a companion of the Earth. So when you quantifier of the infinite, it brings along a copy of itself, sublime, as Kant might say, that it's more than its parts. It is what is its parts. The limit is the sum. And it's in its usual very direct result in theory that the infinity is extraordinary. Ordinary means ordinal. It means regular and rulal by magnitudes to increase, and in an infinite, according to infinite induction and cases for induction. So it's the sort of thing exactly that then gets into the usual foundations of what we call modern mathematics, which is basically 1920s set theory, Zermelo and Fraenkel, Ernst Zermelo and Alfred A. Fraenkel, for whom it is named, ZF set theory. It has sets and ordinals, and it has an ordinary infinity, which is axiomatized there. And it's there because otherwise, when you say for any set, it's a member of the set, it includes itself. And then when you say, oh, well, if a set related to itself, then that would be an inconsistent multiplicity of some sorts, or it leads to just these vagaries. What's vague or unclear needs to be made clear of the impredicativity, that you really can't say that it's predicative, that the predicate applies and is well-defined and goes both ways, has its converses and its inverses and is well-defined, and can be built from these simplest arguments. Or the quantifier ambiguity, to say that, well, for each is like the universal quantifier. What that, it's sometimes ambiguous. You need to break it down for each, for any, for every, for all. Those having different meanings, keeping things simple as necessary when they before were kept so simple by having just where they're conflated together, where they could be extensionally not different. They're not same. So it's not so much more to understand that what goes into ordinary is because of the extraordinary, to arrive at deductively why Zeno's arrow arrives and limit is a sum, and infinity and infinity plus 1 are both infinity, which everybody knows. Okay. So meters per second or seconds per meter. I'm not quite sure how to kind of resolve that. Okay, so the general idea usually is like, well, frame the units so that they're never infinite. And it's kind of funny because then it's like, well, what's the curvature of a straight line? It's like, it's 0. Well, that depends. Like here when we were talking about spatial inversion and that talk after Wertheimer and the Gestalt and all this kind of stuff. What is it? Is it R or 1 over R curvature? Well, that's exactly this sort of idea we have with these projective ideals and the ideas of how to relate these fixed points and singular points that have then in the framings of their contexts, how that can be shrunk to something that then is symmetrical geometrically or has a pattern that so makes for it is like so. So meters per second or seconds per meter is really going to vary, but it's still exactly so that for when it's the non-zero, then a lot of the stuff is easier to solve. That's looking back to the talks about the descriptive differential dynamics. One of the fields these days is called differential geometry, and the idea is it's like, well, we don't have 0 or infinity, so when we talk about these either way, then we can build these submersions and immersions and get forms out because don't have to care, and that's great. It's not complete. It is what it is, as long as its bounds are honestly, in the sense being here, not hypocritically, carried out, then it can be said to be so. That the limit is no different than the sum, and these kinds of things. So that is something that's been ongoing for a long, long, long time, because really what is the infinity was at once both considered the absolute ideal of the quantity in its magnitude, and not a quantity and not a magnitude. It's like you think about Archimedes and his numbers. He's like, well, what's the largest number? He's like, it's not finite. It's like, well, how many numbers are there? It's like, it's infinite. It's like, well, are they infinite numbers? No. Well, see, this is kind of the challenge then to figure out. It's like, these days they talk about a non-Archimedean field. What's that, you might aver? Well, it's got infinite quantities in it. These days there's some talk, and it basically frames it in bounds. And what is practically infinite, or what is effectively infinite? So people who have studied these things generally would be aware of the most usual dichotomy called the potential or the actual. The potentially infinite is that which is unbounded. The actual infinite is that which no bound reaches. All right, fine. And the usual idea is like, well, there's no actual infinity. There's no absolute infinity. And then the potential is that, it's like we talk about bounds, we talk about the lack thereof in numbers. So we build our classical laws of large numbers, we build our expectations for sampling theory and probabilities, all from these. And so the idea of this effective and practical infinity is like, for example, is like, well, we only have a 10 by 10 square. So 100, if you divide any of those numbers by 100, it is going to be less than 1. And you divide any of those numbers that have to fit in any of those numbers by 100 times 100, it will be 0. This is practically infinite. It's a large enough bound that in terms of the radix and the moduli, that being the base of the representation or the biggest divisor, and then the even multiples, whether those 2s or 3s or 10s, usually it's 10s, integral moduli. The idea then that it's all just matters of related rates and related bounds, and then what we call asymptotics, usually in the study of algorithms. Algorithms and data structures are the bread and butter of computer scientists largely, whose goal is to find simple algorithms largely that are having well understood bounds on their runtime and in their two fundamental resources called space, how much storage needs to remain randomly addressable at constant time in uniform memory, and time, which is time, and that's also related sometimes even to watts, like how many hamster wheel turns does it take to crank this algorithm out, But this usually just results time for the algorithm and the occupation of the space according to this given amount of time. Now that's often, in terms of the service of the routine, what is called this asymptotic behavior. It's called big O notation, theta notation, or otherwise where they divide out those things that over time would get amortized away. And so what results is the expression for the big O or theta notation, or usually called big O, which is how long it would take on the order of that. So approximately on the order of that, not by any different than a linear constant, which can then be discarded because it's dominated by the behavior otherwise and the asymptotic of this thing. For the service of a routine, that's the most usual sort of thing, saying, well, I need to go down to the card catalog and get a card and bring it back, and so I expect it to be sorted, and in this such manner, I can expect to reduce the time down to finding where it lives according to a binary search, and it's called log n. It's the greatest facility of all such usual notions of data being sorted, thus that algorithms like Newton's and for root finding basically make it so in the digital and computer science that it's the same kind of thing. So that's asymptotics and algorithmics in large sort. And for the service routine, an example of one. But then you have to get into also all these other things about the bounds and what's practically and effectively enough, which would be a label for something saying, as long as it grows up and doesn't fill the disk, you're fine. Because if it fills up the disk, then it crashes, for example. Just as an example of what are these reasons that go into why what is practically, effectively, potentially infinity and actual infinity are still two different things. And yet we have a very usual law of large numbers that for any given number, there's a number that's larger than it that will be a member of the Archimedean field that will be less than it, and so on ad infinitum, ad absurdum, ad infinitum. So when looking at something so simple as something that just turns over and has, for example, well, what's a vertical line in the Cartesian space? x equals 0 is not it. Y equals 0. How is that to be when it can't be effectively reflected in terms of x? It's multi-valued. Otherwise, a classical function will only have one value input in the domain, one value output in the range. Furthermore, it's a continuous function. Classical functions are generally considered to be continuous functions. So what to do for meters per second and seconds per meter? What to do for meters per second and seconds per meter and meters per seconds per meter? How is it so really that what affects and relates how the things are, that it should so kind of be that they keep their units associated with them and they keep their inversions of units associated with them. So this was the idea, is how many infinitely many degrees does it take to keep in mind how to establish then this kind of stop derivative or what results the power law for power series, but not just like an infinite series all in positive powers, ordinal powers, the negatives of those two. What is it? You know, this is something that isn't always very well explored. But we do get into stuff like, well, how about e to the x plus e to the minus x? At least that's this very, very key and kernel type of thing that gets into a lot of these different things about then functions of these with these particular behaviors that end up being in certain boxes and windows reflective of each other. Why that is so relevant to then the analytical character of this and the ability to establish the inner and outer products in the product spaces of these things, and the spaces of the spaces of the spaces of the spaces of the space of the things. How and why to consider it, to make it like so that getting above the classical, which is perfectly well defined and quite all Archimedean and quite all Euclidean and quite all Cartesian, how to help figure out for these kinds of things with regards to stuff like the identity dimension is one of the ideas here. Framing that x equals 0 and y equals 0 are symmetrical about it. Differential geometry, they don't even exist, and it keeps things simple. And here it's like, well, they tent each other out in a sense. They all have to stay positive. It's missing some of the facility of otherwise having the operators being closed that way. It takes an approach to a practical 0 out somewhere out in the line that then all the differences are still out there in the line, that this point halfway to infinity is the identity dimension analytical origin in a sense. Semi-infinite is usually what you say. It means half infinity. Is that well defined? It's like, well, it varies. It varies who you ask. You ask some of the projective, number theorists. They're like, I will agree exactly that means semi-infinite. Or you say, well, we take the plane and split it in half, and it's like, well, we call the plane infinite, so we'll call half the plane semi-infinite. Okay, so here are these semi-codimensions, x and y, the usual rays, or x, y, z, and ... however many infinitely many dimensions there are in this space. Having that their real origin is still 0, 0, 0, 0, 0. But then each one of the points 1, 1, 1, 1, 1 on out, just that being one point on this identity dimension, reflect how to take what's otherwise usually just like we build squares and products in geometry out in this. And here it's like we've taken squares and cubes and put the roots inside instead. We're inverting the cubes and the roots, and the powers, and the inverse is about and around this. So this is the kind of idea that gets into really going a long ways towards trying to figure out what it is that makes it so that this is the kind of thing that provides the mental device for the object sense and word sense and number sense and time sense. The object sense is geometrical, for the qualia and that this sense of space and time together. is really a thing. So it's almost as if this kind of setup, it's a diagram, identity dimension, it's a device, so it's a thing, has become a great idea fix since really kind of looking at the origins and the study of the integral analysis and the differential analysis, finding those are different schools. They approach things from the opposite sides, from one, the operator basically taking its derivative, the other operator basically taking its integral of functions, all being functions, that just so define over the ranges of these things as they're so representative of what they are, that it's a really pretty great thing then to get into why that this is the kind of thing that will make it so that it's possible to have this kind of analysis carrying up and onward from these tools that then here in the context of meters per second and seconds per meter and meters per second per second per second per second per second per second, which is the infinitely many orders that go into either the topple or the tumble of the domino. When you flick the domino and it topples, does it spin around its center? Does it slide out under its base? Or does it tip over from its top? When you spin a top and it starts to walk, does it weeble or does it wobble? Eventually it falls down. These are the kinds of things to consider with regards to here that it's the dissipative and attenuative, about the oscillative and restitutive, in terms of these notions of their tendencies and propensities again, to help break down in a deconstructive account, not to be a defacing account, but just a deconstructive account, which results recomposing these things back together and helping identify where something that was a concept that was always together, interlinked, and so assured, so extensionally the same, was really two concepts necessarily together. And then as they have the tendencies and propensities conceptually, they form this gestalt again. Why is so? So the stop derivative is basically that idea. Is like, what is that? How do you relate linear and rotational in meeting and parting and accelerating and decelerating and starting and stopping, fundamentally. Starting and stopping. How does it start? How does it stop? Then the other kind of key thing about that, in a sense, is that for the practically, effectively, potentially, actually infinite, there are laws of large numbers, meaning it's like, well, the more you know, the less you don't know, and this kinds of things. Whereas at the same time, there are various laws of large numbers, and so some things have their limit, and they're well defined, and some things go off and vary. For example, the periodic or the cyclical at any particular multiple of the modulus at the time. It could be one or the other of the points at any basically point between -1 and 1. Compared to if you divide that by x as it goes along out, then it's the complementary sine function and its limit exists and is 0. So those are at least kind of well understood and well defined. They'll stay within a range. Kind of like, well, if you roll 2 6-sided dice, the value that's most likely to arrive is 7. But it's still unlikely to arrive. But if you start counting between 6 and 8, now the expected value is going to add up eventually in terms of the counting arguments, make for all the combinations according to the combinatorics. According to the law of large numbers, those being at uniform random, it will result that you could say the expected value is actually in this range of things. Okay. So in the classical probabilities, then a lot of that is built up after the Bayesian. And so he's like, given prior probabilities, we have consequent probabilities. It starts to build correlations and stuff like that. So then there's those kinds of knowledge, and then for laws of large numbers, And then there's Bayesian, the Jeffreys, and the Knightian uncertainty. And whether this is the memorylessness, whether this is the stochastic, whether this is whatever it may well be that causes uncertainty, has that for another complement to the law of large numbers is like the more you know, the more you know, is the more you know, the less. That just being just kind of a casual way to introduce that there are some functions whose behavior belies their finite inputs. These are after the functions that converge very, very slowly, that they'll appear for a long finite time to be within certain bounds and only very slowly have their limit computed. Functions that converge very slowly. There are functions that actually even just kind of belie their finite inputs. And the general idea here is it's like a geometric series that it goes, and it's called asymptotically free, I say. And just like the concept from physics that the most powerful force of strong nuclear attraction holding together protons in the nucleus, the middle is asymptotically free. Here the idea is that a function goes from 0 to 1, and at infinity it drops back to 0. It's not a standard function, not a real function in this sense. It can't be said that the convergence criteria apply to it, usually. There are more than one law of large numbers. There is more than one law of large numbers. There is more than one set of convergence criteria for functions in their spaces according to the topologies, various kinds, that all go together these ways. Just like back to infinity and infinity plus 1, either is infinity, both are. That here is so that their laws of large numbers need this extra standard approach. And that's where a lot of the real utility is going to lie in the future for these things that make it so that real numbers come back out of it, that finite quantities come back out of these things. There are these prototypes of the very most central aspects of these behaviors of the systems of large numbers that really are going to be what comes out of continuum mechanics and continuum dynamics for this practically, effectively, actually infinity. So that's just something that helps to establish that mathematics isn't finished yet. There's lots more to it, to the theory, even today, even in the knowns and the unknowns. Even after the great facility of being able to compute a superscalar finite element analysis on a computer with a 1,000,000-word wide atomic step, and having the granularity and the fineness of an essentially arbitrarily, practically, effectively infinity of these things, that it still doesn't add up to what nature's convergent behavior of the continuum mechanics does. But there is a mathematics yet for this. And so this is a great thing to consider when you get into, first of all, that you're studying analysis at all and arriving at the perfect results of the infinitesimal analysis, the integral calculus. It's not so in the finite. We can approach it with the limit. It must actually reach a limit because we get perfect geometric quantities out of it analytically. A finite element analysis on a computer can be designed to get as close to that as it needs to get, truncating that, providing a number. And with regards to that actually getting around the clock and continuing, it needs sometimes a little push. This is basically the variational methods sometimes, or otherwise what's put into the accoutrement of finite numbers in computation for interval arithmetic, and these kinds of things about where its starting and stopping points may lay, and the limits of finite element analysis while still with the great utility of it and the fact that it just it performs so much that it seems as a panacea. It's yet incomplete. So our analytical methods, algebra and arithmetic and mathematics, still sorts of wins over, counting grains of sand and guesstimating when that's a heap. And it's still something that's easier for the mind to carry within it, because the human mind does not have a million wide fixed superscalar word of a computer architecture that can step instant over instant, single instruction, multiple data, if you will. Or in this case, that the datum is just like a grid, like a connection machine's giant grid matrix, of discrete elements. We have just so simply the facts discovered in mathematics, after geometry, after analysis, after things like the area of Plato's perfect forms, and mathematical constants that are not ratios, so and largely are not available except to this sort of infinitary analysis. That it's a great thing, and it's really what makes it so to separate the mind from the machine. Then that it can be easily so formalized and made it so that in a machine-like manner it can be run up and out such sort of analysis, disambiguating laws of large numbers, disambiguating the impredicativity after quantifier ambiguity, and the transfer principle, making these bridge results where they exist and sussing out when they don't, and for all these inner and outer products and the complementary duals and such notions that result in mathematical fields, and how derivations and models go together for the intentional and extensional. That the plain concepts of what is a practical or effective or potential or actual infinity is for breaking it down, if about that simply, having it, first of all, that things are defined in terms of the unbounded, so that you have a model of the potential infinity. And then if you have something that's practically close enough, fine enough, it's like I when reading my meter stick, I can read down to 30 seconds and a hair. Like you can round up or down either way there. That's accurate. That's practical. Vis-a-vis then the effective, it's like, well, we got a laser ranger, and so we can match those up real great. It's effective. The actual is that it's actual, so it's like, well, we're just staking out a circle, and so as long as we just use a compass, it works perfectly. It will round the edge. These are the kinds of things that get into, then for the potential and actual of the infinity, the practical and the effective insides of those, and the outsides of those. You see, it's always a matter of approximation and estimation. We're humans. We can have our own pristine thoughts, our own object sense, Whereas, well, we know that science affords to us that there are limits and bounds to that, vis-a-vis the discrete, which is Boolean or binary, which is true or false. There are still right and wrong and true and false, especially in mathematics. And then for these other things, it's like, well, somewhere between 0 and 1. But at least we're very, very sure that somewhere between 0 and 1, things go from 0 to 1, vice versa. So these are the kinds of things. 20 years ago or so, I was studying the idea that there's a space, that there's all the zeros and ones have that. If you imagine flipping a fair coin, and it's 0 or 1 for heads or tails. Or you might want to think of it as like -1 and 1, or they're complementary quantities. So if you sum them up, you expect the average to be 0. And the law of large numbers is to expect that you get about the same number of heads and tails over time. But anytime you actually start flipping coins, it's going to arrive at variously a given set of samples, a list of samples. Each one is an event. Usually, each one has its own distinct time. You know, time marches on. Tempus fugit, time flies, and time marches on. So that you can always associate an event with a point in space and time. Right? So, anyways, a sequence of zeros and ones is, you can consider it as by flipping a fair coin, Bernoulli trial. Right? Now, if you think of a real number between 0 and 1, just like you can write it 0.785. So that's 7 in the tenths place, and 8 in the hundredths place, and 5 in the thousandths place. The inverse powers of the radix for the integral moduli, and then the digital moduli, the moduli. So it's a representation. So in 0 and 1, it's 1/2 plus 1/4 plus 1/8, Each of those being on and off is essentially reflecting for any given number between 0 and 1. In binary, there's only two values, on and off here, 0 and 1, that's multiplied by this inverse power. So like if you flip a coin, you say, well, that's either it's got the half bit set or not. It's got the quarter bit set or not. It's got the eighth bit set or not. So one of these numbers basically reflects doing that infinitely many times. It's an unbounded sequence. There's no end to it. So it's got a beginning and no end. It's unbounded. Right? Maybe we won't say it's infinite, but it's potentially infinite. Right? There's no end to it. So any one of these sequences is distinct from any other one because at any given place, it's either the same or different. And so two sequences are only the same if they're the same at every place. Right? So this is as usual. And then in the numbers, there's something that you could say, well, if it's all ones, if it's between 0 and 1, if it's all ones, then that's this infinite sum we just talked about since the beginning. So that's equal to 1. Compared to otherwise, you just put a 1 in front of all that, because all this is behind the radix. Radix is also a name for the decimal point, or whatever is in this usual representational positional notation where it is behind the radix. Okay. Behind the radix, as it were. So from left to right, then, it's in order. Each of these sequences has an order. So you can think of now, besides that they have dual representation of numbers, any sequence that ends with an infinitely repeating digit is like the next higher order. It rolls over, so it's the same as the one that is rolled over. Fine. Okay. But as sequences, they are all just like, each one is distinct. Then you can also imagine that they can be ordered. Zeros first and one. So it's the same as the ordering these sequences as they are the real numbers, their values between 0 and 1. Right? So you can consider this to be the space, which has some extra properties to describe it as an actual space of these things. Because space in mathematics means a thing. It's like you can figure out a basis in the space and get from here to here connected, right? Projected, rather, in the space. Projective in the space goes great. Okay. So you put all these sequences in order, then you can see that you could run out of paper because it's unbounded in length too. Now, it's a key result in modern mathematics that this space is uncountable. It's uncountable. What this means is that any way you take the diagonal of that, you can flip all those bits so it's different from any one of those rows, So the diagonal is not any one of these items in the sequence. It's called the anti-diagonal argument, and it's part of modern mathematics set theory, and it's about the great importance of uncountability to establish an inequality between the measure of the countable, like an infinite, and then this next higher uncountable called a transfinite cardinal, aleph 1 or greater, 2 to the aleph 0, aleph 1 or greater. So anyways, that's one way to look at this. But then you can still think of it in terms of like, well, if you just have but all these things just kind of fit in this set, even though you don't have a function, say, from it. You can say how long or narrow or wide this is. You can still say, well, in any given column, half is ones and half is zeros. Because it's got another kind of property that if you just chop off the first digits and then only take half of it, it results a copy of the same. It's infinite, it's a copy of the same. It's infinite, copy of the same. Or, vice versa here, vice versa, like so. So the idea then, this is, we call this Cantor space. So your Cantor is very famous in mathematics. And in the time of modern mathematics, Russell and Zermelo and Frankel and Cantor essentially kind of fold into what makes ZF set theory as schools of men, okay, including after Dedekind and Cantor, and then Russell and his complement and da, da, da. Anyways, this is it's called 2 to the omega. Is the idea of 2 is 0 and 1. So in this context, you say 2 is 0, 1. And so 2 to the omega is infinity, is like 0, 1 is the language of the alphabet, and that infinitely many is called the language. So this language is called 2 to the omega, or 0, 1 to the omega, and then each word is one of these sequences, like so. So in the space of the words, it's kind of like so. Now the idea of here the line reals or the iota values is that it's not uncountable, but there's not a function. You can reorder it because you can take Cantor space and order it however you want. I mean, it's just however you possibly want to take a number, this integer, and assign it to a sequence, and you can put it in, it's any kind of function from natural integers to these sequences, the numbers. Restricted to 0 for 1 for simplification, and also restricted to 0 to 1 because structurally it has its own sorts, resources, and bounds because of these laws of large numbers about the magnitudes and the quantities. So the idea then is this equivalency function is unique and exists only there, and it's not Cartesian, so you can't reorder it, and only relates to 0 to 1 by itself, because otherwise you can say, well, I can have space of all the real numbers, all the representations that start infinitely many zeros on the front and then just fill out on the integer side, or vice versa here, with respect to how I see it and how it is over here. So this idea of the square Cantor space, a square and compact Cantor space, is it starts at 0, ends at 1. And it only builds in the middle. And then it's defined as just simple, not a real function, yet modeled as a limit, the continuum limit of functions. So it's a thing. So anyways, one of the results in probability theory is that there's an expectation that's built for so, according to this case for so and so and so and so. So I found this identity in it, and I said, well, I'm not thinking about where it comes from. I'm thinking about how it comes down and across in this great Cantor space, square Cantor space, or this sequence of with a beginning and an end that's all self-similar inside and is otherwise just all ordered. It's totally ordered. It's well ordered and totally ordered, which are strong properties in mathematics and demand careful adherence to definition. that then it results from looking at the contents of the space. I was able to say, hey, here's something that looks like a fact and probability. So I was really disabused of this notion because for 1, it's true. For 2, it's true. For 3, it's not true. For 4, it's not true. For 5, it's not true. And it just gets worse. So earlier, there was some discussion of like functions that converge slowly. And then the very idea at all that a function that belies its finite inputs, that it goes up to 1, it's asymptotically free. Well, here's one that's like, it must be asymptotically free, and not only that, but it kind of is like drops off the floor and comes back to this other particular value. So I came up with this expression that's true only in the limit. It's got an infinity on the front of it, so it only works when it's infinity. It doesn't work for any finite number at all. But it's kind of a thing. So I started looking around at this, and because it's just, otherwise it's just a result of expectations, like a law of large numbers will give you this. So I was like, this must be some different law of large numbers. You know? So I started to look at this, and I started to find some derivations of it, because it's an identity, a relation, and it relates the factorial function. Like 10 factorial is 10 times 9 times 8 times ... A million factorial is a million times 999,999 times 999,998, all the way down. It's the falling factorial. Whereas in the factorial, we got rising and falling factorial and like ranges, and they're using all sorts of counting arguments and all sorts of estimations of things by what the factorial is. The factorial is a regular recurring thing. It has its own symbol. It's like the exclamation point means factorial. And the exponential, and what's the exponential? Well, here it's 2 to the something. So it's usually considered on the order of something, like when the variable grows and it's exponential, this thing. So I found a formula that relates the exponential and the factorial in this way. Due to properties of this square Cantor space, this deductively, I was able to arrive at from this other fact, given a law of large numbers and statistics and probability theory, that this thing that looks like it will never, ever, ever do anything but just get farther and farther away from this. It's like so. So I started studying this with respect to Abramowitz and Stegun and the table of integral series and products. And Abramowitz and Stegun was very useful because it gave me some various things like doubling formulas and abilities to find addition formulas among some of these other relations. There are a wide variety of relations known for these kinds of numbers. So I got into that, and then I got into some implicits. I had to kind of fabricate, in a sense, some kind of these implicits of how to make it so that I could start getting numbers out of it in terms of a function and a formula and its parameterizations and its implicits, so resulting that for this formula, as long as it's differential, because one of the inputs is based on this other part of the side of the input, that it will keep it in line. That it's like, it's like I'm tracking, because otherwise it's a blizzard and a snowstorm, we would just get lost. But as long as we have something that can kind of keep it like on the same course, then, it's the path. It's like trying to climb over the Alps or something like that. And you hope you find one of those, little waving flag things going along where you're supposed to go, right? Metaphorically. So I kept at this for quite a while, and I started finding a bunch of different stuff. I'm like, well, I got to find these coefficients. I got to explode all these combinatorics. I got to find all these things. I got to find all these closed forms. I got to find all these Stirling numbers, their closed forms. Like counting arguments are like n choose k, Stirling cycle numbers, Stirling subset numbers, how many can there be? All these kinds of things. How is that symbolically? How is that algebraically? How is that in laws of large numbers? It's pretty cool. And so at some point in time, I ended up with via this kind of algebraic manipulation, I ended up with a formula for factorial function. And so it's like, well, what is it? It's like, well, it's kind of an estimate for factorial. It's an approximation. And it's after this sort of development. And it's pretty cool. And so now it's like Stirling found this. Stirling has found this approximation for factorial, and Hadamard has found an approximation for factorial. The gamma function sometimes is called. Factorial is for integers. Gamma is like if you interpolate it for the real numbers between the integers, the output is a real number between the integers. So I found this, and it's pretty accurate and close. I've sent it up to one of the AI systems, and they're like, no. I was like, look, and they're like, well, yeah. So it's very surprising because it's similar, just exactly when we had that development, there's some of the convergence criteria for these things to exist. And one of the fellows on the board, whereas I was writing all this out, he said, well, by this convergence criterion, that is not so. I said, well, by that convergence criterion, Stirling's is also not so. So it's a good example of something that is known to be accurate, its error terms are kind of modeled and it's kind of understood as behavior. Some convergence criteria are related to some laws of large numbers simply don't apply. They converge too slowly, or they have what otherwise is a behavior that makes it like so. So I was pretty happy about this. I wrote that up about 20 years ago, and I've been trying to think about it a little bit from time to time. And it's part of then this whole notion of what are the laws of large numbers, then to arrive at how to get up in these actual and infinite bits, and then how to explain that in terms of effectively and potentially, and actually in this the infinite. It's about continuum mechanics and continuum dynamics, laws of large numbers and convergence criteria in the analysis. So for meters per second or seconds per meter, that's not really right in line with this idea of the identity dimension and the ability to try and figure out where these singular points and fixed points live for all these usual integral transforms. But it is kind of an example of what gets into some higher apparatus of mathematics, which is based upon the spaces, which is based upon these complementary duals. I'm looking both ways to arrive at this inside. What now is a function, for example, and then a bunch of other ones spew off of them, and they emit numbers that start looking good. So that's something that it just based on this course of analysis is like, this is mathematics I found, and I'd really like to know a lot more about, because most people give up right away when they're told you'll be wrong forever. And I would too, if I hadn't, kind of walked up behind the guy. I was like, are you sure there's nobody behind you? So anyways, this amuses me quite thoroughly. So yeah, meters per second or seconds per meter is really just what's apropos. And pretty much whether you're going or stopping, these are things that basically indicate what is the critical resource that must be conserved. Laws of large numbers. They reflect common principles that there is an unbounded, there is a sublime, there is infinity. It's got all its behavior, and it's perfectly fair to use the word metaphorically because it has to fulfill all of that. And in the formality, we can get into this potential and actual for the unbounded, and the completions of things when they're to fill out to the unbounded, and the limit, the infinite limit, the continuum limit. It's great. The potential then into the effective and practical. It's applied. It's concrete. That these can go a long way then for making some of these fundamental pieces that go into the continuum dynamics. They go into, it's part of the foundations of mathematics and physics for the 21st century.